Welcome students. It's been quite a many days since I uploaded the last lecture. My apologies for the delay. If you want to revisit the first lecture, you can do so from this link over here. Nevertheless, the uploaded PDF with this lecture includes the earlier lesson as well. So let's now start with today's lesson. In this lesson, we will be mainly talking about three things: basis, linear independence, and dimension of a vector space. Now please be alarmed with the order in which the topics are coming. This is an alternative approach that I took to cover these topics. The main reason for which is being the natural flow of the concepts. Also, as a bonus, we get many of the important theorems and results as mere corollaries. So let's start our discussion. Now let W be a subspace of a vector space V. Now considering W as a subset of V, we see that the span, linear span of W is itself. This observation tells us an important fact, that every subspace can be considered as a span of a subset. Now if you remember that a span of any set was a subspace of the vector space, and here we see that for any subspace as well, that subspace can be considered as a linear span of itself. So therefore there is a one-to-one correspondence between any subspace and subspaces of the form linear span of a set, right? So while studying subspaces of a vector space, one only needs to consider subspaces of the form linear span of a set, subset S. Naturally, the generating set S is supposed to carry major information about the subspace generated. But in this example, we saw that a generating set is not unique. Let's see the example. This is the example we talked about in the last lecture. You can just revisit the last lecture video once again, or let us just have a quick recap over here. Here we have a set S1. So here we are main vector space, underlying vector space is R3 over the field R, and the set we are concerned, one of the sets we are concerned here is this S1. What is this? This is nothing but the y equal to x plus 1 straight line on the xy plane, on the z equal to 0 plane. Okay, so this is just the line y equal to x plus 1 on the xy plane, and we are talking about this entire thing in R3. Fine. We found out that the span of linear span of S1, this will be linear span of S1 is nothing but the xy plane. Now, on the other hand, if we consider S2 to be this particular set, the unit vector along x-axis and the y-axis, then the linear span of S2 is also xy plane. Okay, so this was our example. Now let's go back to our discussion. So in this example, we saw that a generating set is not unique. Both S1 and S2 in that example were generating the same span xy, same span xy plane. Moreover, their sizes vary in an infinite proportion, and none of them is a subset of the other. Over here, the size of S1 is infinite. It is a straight line, all the points on the straight line y equal to x plus 1 on the line, on the plane z equal to 0, xy plane. So the cardinality of S1 is same as cardinality of R. And over here, S2 is a finite set having only two elements, right? So size-wise, they vary to an infinite proportion, and none of them is a subset of the other. Now, which one of S1 and S2 is more convenient choice for a generating set of xy plane? For its smaller size, the obvious choice is S2 in this case. We are able to generate the entire plane, xy plane, using two vectors. So why will we need the entire line with uncountably infinitely many vectors over there. So obviously S2 is a obvious choice to be chosen as the choice for a generating set of a XY plane. So a sensible question to ask at this point is, given a subspace of a vector space, how small can a generating set be? We'll find an answer in this section. Before we proceed further, let us list a couple of properties of linear span, the proofs of which are very easy and left as exercises. Let us see these exercises a little carefully, because we are going to use these properties in our coming in this lecture. So V is a vector space and S1, S2 are two subsets of V. Then if S1 is a subset of S2, S1 is contained in S2, then linear span of S1 will be contained in linear span of S2. Fine, this is first one. And the second one is, if a vector alpha is there in the span of S1, then linear span of S1 union that vector alpha is same as linear span of S1. So you do not get anything extra if you add a vector alpha from its span itself. Okay, so alpha is coming from span of S1, and if you add that vector alpha to S1, you do not get anything extra in the linear span of the new set. Fine. So these two exercises we are going to use in today's lecture. So let's proceed. We start by observing a key fact in that example, in that last example over here. So if we choose only the points with rational coordinates from S1, remember S1 was this line y equal to x plus 1 on the xy plane. If we choose only the rational coordinates, then by the same procedure done over here, we'll be able to show that linear span of S1 dash, let's say, will still be xy plane. Okay, the points rational coordinates from S1, that is the points x, comma, x plus 1, comma 0. 0 because it is in the xy plane. So x comma x plus 1, that is the line y equal to x plus 1, and where the point x is varying over q, the points with rational coordinates on that line. So we get the same span as xy plane. We have removed, now observe carefully here, we have removed an infinitely many number of points from the generating set S1 and still are able to retain the same span. Okay, we have removed all the points with irrational coordinates, and they are actually uncountably infinitely many in number. So we have removed an infinitely many number of points from the generating set and still are able to retain the same span. But on the other hand, we cannot delete a single point from S2 and keep the span intact, right? What is S2 was the unit vector along x-axis and the unit vector along y-axis. We cannot remove any single point from this one and retain the same span. So this observation motivates us to define the following definition of a basis. Okay, let V be a vector space over a field F. Let S be a generating set of V, that is linear span of S is equal to V. Then S is called a basis of V if no proper subset of S generates V. Alright, now one point I must utter over here, that in this definition we have moved from our we have moved our discussion from a subspace to a vector space, because a subspace, the vector space itself can be considered as a subspace of itself. So this is the subspace, adopting the subspace in our discussion was just for the motivation purpose, but we are doing this entire thing for a total vector space only. Okay, so here we move from subspace to vector space, and we do not lose anything because the entire space is a subspace of itself. Okay, so a basis is the smallest generating set. For example, in the concerned example, in the last example, S1 was not a basis. This entire line was not a basis, but S2 was definitely so. Okay. So a few remarks. A basis is a minimal generating set of a vector space, the smallest generating set of a vector space. The guarantee of existence of a basis for any vector space in the general setup is beyond our course, but we will see a proof for a special class of vector spaces. All right, this existence of a basis, a minimal generating set, the proof is definitely there. Sort of an equivalent proposition to axiom of choice in John's lemma, and we are not going into that, but we'll see the proof for a special class of vector spaces in this lecture. Now, by our above discussion, we do understand that it is not easy to extract a basis from a generating set, right? See, from S1 we had removed infinitely many points and still are left with infinitely many points, and here in S2 just by the mere choice it turns out to be a basis. So if we start with S1, that is not a very easy thing to do, to reach at a basis from there. So we do understand that it's not easy to extract a basis from a generating set. So to make our lives easy, we take another route to reach to a basis, that is through linearly independent sets. Now, what is that? Let V be a non-trivial vector space over a field F. Non-trivial means it is not only the vector theta. The only null vector also forms a vector space, that is a trivial vector space, and we are not very much into that because a trivial vector space has a basis defined as the null set. Okay, and things are not that much interesting over here. So let V be a non-trivial vector space over a field F. Choose a non-null vector, non-zero vector alpha in V. Now, if a linear span of alpha is V, then alpha is a basis of V because we cannot reduce it to anything else. So, if not, choose another vector beta and consider the linear span of alpha and beta together. At this stage, let us be a little pragmatic. Now, understand this thing that we are trying to reach to a basis, to a generating set of a vector space, of the vector space. We started with a non-zero vector alpha. We did not succeed. So we are looking for another vector. Okay. Now let's see, where do we want to choose this another vector from? If I choose beta from span of alpha only, then by that exercise, the linear span of alpha beta will not give us anything extra. That will be linear span of alpha only, and we gain nothing extra over here. So let us agree to choose beta from outside of the linear span of alpha. Since we are assuming that alpha does not span V entirely, so there are definitely vectors which are outside of the linear span. So choose one from there. Then we have the linear span of alpha is a proper subset of linear span of alpha comma beta. This notation, let me explain. This is a proper subset notation. This is a subset and this is not equal to. Okay, so this is proper subset. So then we have linear span of alpha is a proper subset of linear span of alpha comma beta. Now, can beta be a basis? Because when we are talking about alpha beta can be shrunk to alpha or beta. shrinking to alpha doesn't work. That's what we have seen over here. But can the shrinking to beta work? No, because if so, then linear span of beta should be V, and since alpha is a vector, alpha should belong to linear span of beta. But this implies alpha is equal to C times beta for some non-zero scalar C, because alpha and beta both are non-zero vectors, which in turn implies beta is equals to C inverse alpha. C is not zero, so C inverse exists in F. So beta is equals to C inverse alpha, and then beta is a vector in linear span of alpha, but we have chosen beta from outside of linear span of alpha. So we arrive at a contradiction. So beta cannot be a basis of V. So the set alpha beta together goes a little extra mile towards being a basis of V. If linear span of alpha beta is equal to V, it is a basis. Otherwise, for the same reason as before, choose a vector gamma from outside of the span of alpha beta. Then linear span of alpha beta will be a proper subset of linear span of alpha beta gamma. If linear span of alpha beta gamma is equal to entire V, it is a basis. Otherwise, we continue in the same fashion. Okay. At each step, we are constructing a set which is called a linearly independent set, the precise definition of which is given below. Let V be a vector space over a field F, and S is a subset of V. Then S is called a linearly independent set if for every vector alpha in S, alpha does not belong to linear span of S minus alpha. So if you remove alpha, if you remove a vector from there, you are definitely going to lose some vectors from the linear span. Okay, for every vector alpha in S, alpha is not present in the linear span of S minus alpha. So see over here, we chose beta from outside of linear span of alpha. So this linear span of alpha, this alpha is basically the set alpha beta minus vector beta, and that is exactly what is saying over here. So for every vector alpha from S, alpha is not present in the linear span of the set minus the vector concerned. Okay, then it is the linear independent set. A subset which is not linearly independent is called as linearly dependent set. An immediate consequence of this definition is the following proposition. If let V be a vector space over a field F, a subset S is a basis of V if and only if S is linearly independent and LS is equals to V, right? This was the definition of basis you knew, and this comes as a proposition, and this comes as a follows almost immediately from the definition of basis and the definition of linearly independent set. The subset S will be a basis if it is linearly independent. That means no proper subset of this generates the same span. That was the definition of linear independence. See, no proper subset. This is the largest possible proper subset S minus alpha, and it does not have the vector alpha in it. So definitely that means this does not generate the entire space V. That is what a basis is. So basis is the smallest generating set. So if it is linearly independent and LS equals to V, then it is a basis. Remark, since you are doing this course for the second time, the last two definitions may seem a bit made up at first. But you can already see the fruit of in the last proposition. We have proved that a minimal spanning set is linearly independent. Also, we will define the other usual definition of linearly independent sets and establish the equivalence of these two forms, which is motivated by the following example. Example is this one. Let alpha be this vector 1 to 1. We are doing this in R3. Alpha is 1 to 1, beta is 2, 3, 2, and gamma is the vector 5, 0, 5. Then we have this relation, gamma is equals to minus 15 alpha plus 10 beta. So therefore, gamma is a vector in L of alpha beta, and therefore the set alpha beta gamma is linearly dependent. Right? Now, to find this coefficients minus 15 and plus 10, this is a tiresome job, right? So this is not that easy to find out. So this example shows that our definition of a linearly independent set, though naturally adapted, definitely, is not very practical to check for linear independence in real situations. To deal with that, we have the following equivalent characterization of linear independence, and that is this characterization you know as the definition of linear independence so far. So this is the theorem. Let V be a vector space over a field F and S is a subset of V. Then S is linearly independent if and only if for any choice of vectors alpha 1 to alpha n in S, the linear relation C1 alpha 1 plus C2 alpha 2 up to Cn alpha n equal to null vector is true only if all the scalars are C1, C2, Cn are 0, right? This is the definition of linear independence, you know, and here we are proving the equivalence of these two definitions. Let's see the proof. We'll prove this with contrapositive arguments. Sufficient part. So that means we assume that that S is this condition is true, and we are going to show that S is linearly independent. So we want to show that the condition implies linear independence. So by contrapositive argument, we are going to this translates to not linear independence implies not the condition, right? So we assume that S is not linear independent. So then there exists a vector alpha such that alpha belongs to linear span of S minus alpha, our definition of linear independent set. Hence, there are vectors beta 1 to beta n from S, none of which is alpha, and scalars C1 to Cn such that alpha is expressed as linear combinations of beta 1 to beta n. Alpha is equals to C1 beta 1 up to Cn beta n, right? This is what it means by alpha belongs to L of S minus alpha. Okay, so we have got some vectors in S minus alpha. Those vectors are beta 1 to beta n, which for which a linear combination of which gives me alpha back. So, but this implies C1 beta 1 plus up to Cn beta n plus minus 1 times alpha is equals to theta. Okay, so this means the coefficient of alpha is minus 1, which is not 0. So this contradicts the given condition. The condition says that this kind of a linear combination equal to theta is only true for the choice for the only choice of scalars all 0. So here this one is again a linear combination in S, but here we have got a coefficient which is not 0, so it contradicts the given condition, right? So therefore contrapositively, so that means we assume that S is not linearly independent, so that means the condition does not hold true. So contrapositively, if the condition holds, then S must be linearly independent, right? Okay, necessary part. let the condition does not hold. Okay, here also we are going to use the same contrapositive argument. So here let the condition does not hold. Then there are vectors alpha 1 to alpha n in A such that the linear relation C1 alpha 1 plus C2 alpha 2 up to Cn alpha n equal to theta is true for some choice of C1, C2 up to Cn, not all of which is 0, right? Let Cj is not 0. Fine, the jth scalar is not 0. Then Cj inverse exists in F, and hence alpha j, we can write this entire thing over here. We can write this entire thing over here in this way. Alpha j is equals to minus Cj inverse times the rest of the part. So minus Cj inverse C1 alpha 1 minus Cj inverse C2 alpha 2, and it goes on like this. Here we see we do not have alpha j over here. Alpha j minus 1 is there, alpha j plus 1 is there. We do not have alpha j. Alpha j is over here. This is just a rearrangement of this relation over here. Fine. So now what is this? This is basically, and I have just written this entire thing in notation, in summation notation. K runs from 1 to n, k not equal to j. Ck alpha k multiplied with minus Cj inverse, and this is, if you call this minus Cj inverse Ck as your dk, then this is your this summation is like this: sigma dk alpha k, where k runs from 1 to n, and definitely k is not equal to j. But this relation shows that alpha j is in the linear span of is a linear combination of alpha 1, alpha 2 up to alpha n, except alpha j. So alpha j is a linear is in the linear span of all these things, and this one is actually a subset of linear span of S minus alpha j. Right? Here all these vectors are coming from S, right? And so this linear span, and so this set is a subset of this set S minus alpha j. So by that exercise we recorded there, this relation holds true. This linear span will be a subset of this linear span. So alpha j belongs to linear span of S minus alpha j. That means S is not linearly independent. So that means condition does not hold means S is not linearly independent. So contrapositively, if S is linearly independent, then the condition holds. Fine. Okay. So we have proved the necessary and sufficient condition. We have come back to track what we knew in our last year's lesson. The characterization of the definition, of linear independent set. So we have proved the equivalence of these two definitions. So now when we have the equivalent characterization of linear independence, it remains for an easy exercise to check that any subset of a linearly independent set is linearly independent. Okay, that is very easy from that characterization. But nothing can be said about a superset. If you decrease a linearly independent set, it remains linearly independent. But if you increase, you cannot say something very confirmly. So it may or may not be linearly independent. Now, taking cue from our discussion about reaching a basis through construction of linearly independent sets of increasing sizes, we may intuitively suspect that there should exist a maximal linearly independent set which cannot be increased any further, keeping the linear independence of the set. So there should exist a maximal linearly independent set. This is a suspicion. And that maximal linearly independent set should also be a basis. So we start with we investigate this suspicion, this intuition formally. So let us define what is a maximal linearly independent set. Let V be a vector space over a field F and S is a subset of V. Now S is called a maximal linearly independent set if any proper superset S1 of S is linearly dependent, is not linearly independent. Okay, this notation is same as the other one I explained there. This is superset and strictly not equal to. So this is a proper superset. S1 is linearly dependent, right? So S is the maximal linearly independent. We cannot increase that any further. Now we claim the following, that V be a vector space over a field F and S is a subset of V, then S is maximal linearly independent set if and only if it is a basis of V. So what we were suspecting over here, our intuition is actually true. So this theorem guarantees that. Let's see the proof. And now, before proof, if we prove this theorem, understand this thing, that whenever we are talking about this maximal linear independent sets, minimal spanning sets, all these things, they require some guarantee of their existence, right? We are still talking about a general vector space. Since you know the dimension, I am saying this can be infinite dimensional. So this maximal linearly independent set or minimal spanning set, they require the guarantee of their existence. So we have assumed the guarantee of existence of a basis over there. Now understand this thing. Here also we need the guarantee of maximal linearly independent set, but we can bypass this by this theorem, that if this theorem tells us that a maximal linearly independent set is always a basis, then the assumed existence of a basis will also guarantee the existence of a maximal linearly independent set. Agreed? So this is sort of this arrangement we need to make. With this in mind, we move forward to prove the theorem. Okay. So let S be a maximal linearly independent set. We need to show that S is a basis. To say S is a basis of V, we only need to show that linear span of S is equals to V. We do because by definition of linearly independent sets, no proper subset of S would generate the same span as of LS. So so LS will be equal to, so then S will be a basis if S is linearly independent and spans the entire set V. Henceforth, making it a basis. Fine. Assume the contrary. So that then V minus LS is not phi. Okay. So S is a S is a maximal linearly independent set and it does not span V. So there exists some vector in V minus LS. And consider S1 as S union beta. Beta is a vector from outside of the linear span of S. Then S1 is a proper superset of S and hence is linearly dependent because S is maximal linearly independent set. Therefore, there exists vectors alpha 1 to alpha n and beta. We can always stuck that in from S1 and scalars C1 to Cn and C, not all 0, such that C1 alpha 1 plus C2 alpha 2 up to Cn alpha n plus C beta is equals to theta, right? S1 is not linearly independent, so we have got this relation satisfied for scalars C1 Cn, C1 up to Cn and C, not all of which are 0. We claim that C is not 0 because otherwise we will have vectors alpha 1. If C is 0, then this means C1 alpha 1 plus C2 alpha 2 up to Cn alpha n is equals to theta, and C1 to Cn, not all of which is 0. So that contradicts that the set S is linearly independent. right? Because alpha 1 to alpha n, all of them are coming from S. S1 only has beta extra in it. So so we'll have vectors alpha 1 to alpha n from S and scalars C1 to Cn not all 0, such that C1 alpha 1 plus C2 alpha 2 up to Cn alpha n is equals to theta. A contradiction to the fact that S is linearly independent. So C has to be non-zero. But C not equal to 0 implies C inverse exists in F in the field, and hence we can write this thing beta, this relation over here as beta is equals to this way, minus C1 C inverse C1 alpha 1 minus C inverse C2 alpha 2 up to C inverse Cn alpha n. But this vector over here, this is a vector from linear combination of the vectors from S. So this vector belongs to LS. So therefore beta belongs to linear span of S. That is a contradiction because we have chosen beta from the outside of linear span of S. So this is a contradiction. So hence LS has to be equal to entire V, and therefore S is a basis. Conversely, let S be a basis. Then LS equals to V, and no proper subset of S generates V. That is our definition of basis. Remember, we will first show that S is linearly independent. Choose alpha arbitrary from S. Call S1 as S minus alpha. Fine. Now, if alpha belongs to L of S1, then L of S1 is L of S1 union alpha. By that exercise, remember, alpha is we are choosing alpha from we are assuming alpha from linear span of S1. If we attach alpha to that S1, we do not get anything extra in the linear span. So this is a linear span of S1 is linear span of S1 union alpha, and S1 union alpha is nothing but S, and this is LS, so this is equal to V. This means L of S1 is equals to V, but S1 is a proper subset of S. So a contradiction to the fact that no proper subset of S generates V. Hence, alpha does not belong to L of S1, that is L of S minus alpha. Hence, S is linearly independent. Okay. So now next we will show that S is a maximal linearly independent set. Let S2 be a proper subset of S. Then S2 must contain a vector beta from V minus S, of course. Without loss of generality, assume S2 is equals to S union beta. Okay. Why this is without loss of generality? Because we have chosen S2 to be any proper superset of S. So that means S2 has at least one vector, and this is the least proper superset we can think of. If the thing is true for S2, it will be true for any superset of S. So without loss of generality, assume S2 is equals to S union only one vector beta. Fine. But then V is equals to L of S is equals to L of S2, because L of S2 has nothing, nowhere else to go but to be entire V. S is a subset of S2, so linear span of S will be a subset of linear span of S2, but the linear span of S is entire V, so linear span of S2 has to be entire V as well. So this means beta belongs to linear span of S2 minus beta, right? S2 linear span of S is S2 minus beta, so beta belongs to linear span of S2 minus beta, showing that S2 is linearly dependent. So hence S is a maximal linearly independent set. So therefore we have proved that a maximal linearly independent set is same as a minimal spanning set is what is called a basis. Fine. So far we have seen that a maximal linearly independent set is always same as a minimal generating set. And this fact holds true in any vector space. Now let us turn our eyes to something particular in nature. We call a vector space finitely generated if it can be generated by a finite set of vectors. For example, in this example, Pn, where Pn was polynomials of degree less than or equal to n minus 1 with real coefficients. This Pn is finitely generated vector space. This is finitely generated. Whereas in the next example, Rx, the set of all polynomials, is not finitely generated. Pn is finitely generated because a basis of this is the polynomials 1, x, x square, x cube up to x to the power n minus 1. So this n many polynomials can generate entire Pn, but we cannot have a finite set which can generate all polynomials with real coefficients. Okay, so Pn is finitely generated where Rx is not finitely generated. The subject linear algebra mostly deals with these finitely generated spaces. So from now on, let us be concerned about them only. In a finitely generated space, things are much easier to handle. For example, we can have a proof of the existence of a basis for a finitely generated vector space. Remember, we talked about we are going to see a proof of this existence of basis in a particular case. This is the particular case of finitely generated vector spaces. We are going to see a proof of the existence of a basis. So this is a theorem that exists a basis for every finitely generated vector space. Proof. Let V be a finitely generated vector space over a field F. If V is equals to the trivial vector space, then the empty set is a basis of V. Otherwise, let S is equals to alpha 1 to alpha n be a finite generating set of V. Okay. If no proper subset of S generates V, then S itself is a basis. That is our definition of a basis. Otherwise, if there is some proper subset of S generating V, choose that one and call that S1. So S1 is a proper subset of V, a proper subset of S, be a generating set of V. If no proper subset of S1 generates V, then S1 is a basis. Otherwise, choose S2, a proper subset of S1, be a generating set of V. Continuing in this fashion, after at most n minus 1 many steps, because we have n many vectors over here, after at most n minus 1 many steps, we arrive at a minimal generating set Sk of V. Okay, this may not be Sn minus 1 because we S1 can be by removing 2 vectors from S, S2 can be removing 4 vectors from S1. So at most n minus 1 many steps are required, and the a minimal generating set may not be Sn minus 1. It at most Sn minus 1, but in general it is Sk. So we arrive at a minimal generating set Sk of V, because after that we go for the empty set, and which generates nothing but the trivial vector space, and V is not trivial. So we arrive at a minimal generating set Sk of V, that is no proper subset of Sk can generate V, making Sk a basis of V. Okay, a straight and simple proof of this thing. There exists a basis for every finitely generated vector space. Now, we have seen that basis of a vector space is not unique. But a striking fact about them is that all of them have exactly same number of elements in them. The proof of this fact is particularly easy for finitely generated spaces. We establish it in the following way. We start with the replacement theorem. If V is a finitely generated vector space over a field F and S is alpha 1 to alpha n is a basis of V, then let a non-zero vector beta is expressed as beta is equals to C1 alpha 1 plus C2 alpha 2 up to Cn alpha n for scalars Ck, C1 up to Cn. If a scalar Cj is not 0, then alpha 1 to alpha, this will be alpha 1 to alpha j minus 1, not alpha I minus 1. Alpha 1 to alpha j minus 1, beta alpha j plus 1 to alpha n. This is another basis of V. That is, beta can replace the vector alpha j in the basis S. Proof will show that this set over here, provided this is alpha j minus 1 and alpha j plus 1, this set is basically nothing but S, this is my S, minus alpha j union beta. So here just beta has replaced alpha j. So we are going to show that this one is a basis by showing that this is linearly independent and L of S1 is equals to V. Now L of S1 is, see, this is dk sigma dk alpha k runs from 1 to n, k not equal to j, plus d beta, where d and all these scalars dk's are varying in f. That is what L of S1 is. Okay, so this is the linear span of S1, sum of dk alpha k, where dk's are varying over f, the field f, k is running from 1 to n, k not equal to j, and d is the scalar associated with beta. Fine, then what is this? This is same as I have just written, this is same as the first term is unchanged. Now beta is nothing but summation k runs from 1 to n, ck alpha k. That is the definition of beta over here. So this is d times k runs from 1 to n, sigma ck alpha k. D and dk's are varying over f. So this is, I've just collected things together, dk plus d times ck. Remember, ck is a constant and d and dk's are varying. Dk plus d times ck times alpha k, k is not equal to j, and d times cj alpha j. Okay, from here I have collected everything over here which are not equal to j and collected over here, and the remaining is d cj alpha j. The jth term is remaining here, d cj alpha j. Fine. Now this one is sigma xk alpha k, where xk is varying over f. So xj is d times cj, and the rest of the xk is dk plus d times ck, where k is not equal to j. Now remember, now understand something, that here d and dk's were varying entirely over f, and so therefore dk plus d times ck will also vary entirely over f. So xk will vary entirely over f. Okay, no point of f will be left behind. But this is nothing but L of S. Okay, alpha 1 to alpha n, this is L of S, and this is equals to V. So L of S1 is equals to V. So S1 also spans V. Next, to show S1 is linearly independent. So consider the relation, this one. We are going to use the if and only if criteria for linear independence. So x1 alpha 1 plus x2 alpha 2 up to xj minus 1 alpha j minus 1 plus x beta plus xj plus 1 alpha j plus 1 up to xn alpha n equals to theta. X and xk are scalars from f. So this again, this implies, again, we have written beta, we have written this beta in terms of alpha. So this is k runs from 1 to n, k not equal to j, xk alpha k plus x times this beta over here, k runs from 1 to n ck alpha k, this is equals to theta, and this is grouped together again like this, xk plus xck alpha k plus xcj alpha j equal to theta, which in turn implies xcj equal to 0, and all these things, all these coefficients are 0, because this one alpha k, k runs from 1 to n, k not equal to j, and alpha j here separately, all these vectors are from S, and S is linearly independent. So so this relation must give me all these coefficients, scalar coefficients must be separately 0. So xcj equal to 0 and xck is equals to 0 for all k not equal to j. But xcj equal to 0, and cj not equal to 0. Remember, beta replaced alpha j because cj was not 0. Cj not equal to 0 implies x equal to 0. So therefore, if you put x equal to 0 here, then xck becomes 0 and xk becomes 0 for all k not equal to j. So therefore, x equal to 0, and for all k not equal to j, xk is also 0. So therefore, S1 is linearly independent. Hence, by this proposition, the this one basis is if and only if linearly independent and LS equals to V. So S1 is a basis. Fine. So we have proved the replacement theorem. So with this theorem at our disposal, we move forward to prove the following important theorem. If V is a finitely generated vector space, then any two bases of V have same number of elements. Okay? You see where we are heading to. Proof. Let S1 be alpha 1 to alpha n and S2 be beta 1 to beta r, be two bases of beta V. Then none of alphas or betas is a null vector because they are elements of basis which is linearly independent. So none of them can be null vectors. So then by replacement theorem, beta 1 can replace a vector in the basis S1. Beta 1 can replace a vector, any vector in this S1. So without loss of generality, let us assume beta 1 replaces alpha 1 in S1. That is B1, beta 1 replaces alpha 1. So beta 1, alpha 2, alpha 3 up to alpha n is a basis. Again, as beta 2 not equal to 0, beta 2 can replace a vector in the basis B1. We claim that beta 2 can replace one of the alpha vectors. It does not necessarily, it need not necessarily replace beta 1. It can replace one of the alpha vectors. Because if beta 2 is equals to this one, beta 2 is expressed as a linear combination of these basis vectors, C beta 1 plus C2 alpha 2 up to C3 alpha 3 up to Cn alpha n, then, and for all of ck is equals to 0, okay, because I mean here beta 2 can replace those vectors for which the scalar coefficient is not 0. So we are claiming that it can replace one from over here, C2 alpha 2 up to Cn, one from over here, alpha 2 up to alpha n. So for that we need to show that at least one of C2, C3 up to Cn is not 0. So while claiming that, otherwise, if we choose all of C2 alpha, if we choose all of C2 to Cn, all these scalars to be 0, then beta 2 is C times beta 1, right? Showing that beta 2 is in linear span of beta 1, which is a subset of linear span of S2 minus beta 2, a contradiction to the linear independence of S2, right? Here again we have used the exercise we recorded earlier. So hence at least one of these CKs are not 0. That is, beta 2 can replace one of these alpha vectors in the basis B1. Without loss of generality, I assume beta 2 replaces alpha 2, and B2 is beta 1 beta 2 and then alpha 3 alpha 4 up to alpha n is the new basis. Again, as beta 3 is not 0, beta 3 can replace one of the vectors in the basis B2, and in fact specifically one from the alpha vectors for the same reason mentioned above. Without loss of generality, assuming beta 3 replaces alpha 3, that B3 be a new basis thus formed, beta 1, beta 2, beta 3, and then alpha vectors. Inductively, at kth state, beta k replaces alpha k and makes the new basis bk as this one, beta 1 to beta k, and then the alpha vectors, rest of the alpha vectors. Now, if R is greater than n, then after nth steps, after n steps, Bn, beta 1 to beta n will become a basis of V. It will replace all the alpha vectors from the basis S1. But since R is strictly greater than n, there are definitely some more vectors in S2, more beta vectors in S2. So Bn will be a proper subset of S2, a contradiction to the fact that S2 is a basis, because by replacement theorem, Bn will also become a basis. That means it will generate V. That means it is a proper subset of S2 which is generating V. That is a contradiction to the fact that S2 is a basis. So that means R cannot be greater than n. R is less than or equal to n. Similarly, if we replace the beta vectors in the basis S2 by the alpha vectors from S1, so we were replacing the vectors from S1 by the vectors from S2. Alpha vectors we were replacing by the beta vectors. If we do the opposite now, if we replace the beta vectors by the alpha vectors, then uttering the exact same argument as above, we arrive at the conclusion n is less than or equal to R. Therefore, R equal to n, and this proves the theorem. So, any two bases of a vector space, of a finitely generated vector space, has the exact same number of elements. This last theorem enables us to have the following definition of what is called a dimension. That V be a finitely generated vector space, the number of vectors in a basis of V is called the dimension of V. Remarks? If V is a vector space of dimension n, we write dimension of V is equals to n. In the light of this definition, from this point onwards, a finitely generated vector space will be called a finite dimensional vector space. If dimension of V is equals to n, then we say V is a n-dimensional vector space. Now see the magics. Also, after the last theorem, a number of corollaries are at our disposal as well. These corollaries were important theorems in the earlier approach. First one, if V is an n-dimensional vector space, then every maximal linearly independent subset of V has exactly n elements. Maximal linearly independent subset of V is a basis. Basis has got n elements, and so therefore maximal linearly independent subset of V has exactly n elements. Extension theorem as a corollary. V is a finite dimensional vector space, then every linearly independent subset of V is either a basis of V or can be extended to a basis of V, right? Because linearly independent subset, it cannot go the maximal linearly independent subset, and that there we have a threshold finite dimensional over there. Next corollary, V is an n-dimensional vector space, then every subset S of V with more than n elements has to be linearly dependent. It's just sort of a corollary of this one, extension theorem. Next, delation theorem as a corollary. V be an n-dimensional vector space if V is generated by a subspace S, subset S, which is more than n elements, then a proper subset of S can also generate V, because that is, some vectors can be deleted from S, because S will not be a basis then. More than n elements, so that means it is not a basis. That means a proper subset of S can also generate V. That is, this is a delation theorem. And last,
If V is an n-dimensional vector space, then no subset with less than n elements can generate V. Okay? So all these corollaries, which were good standing theorems or in the earlier approach, they are coming as a mere corollaries, very simple, with simple proofs. So that is why I chose to adapt to this approach. Tell me how did you like this approach? And thank you for your patience.